Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Good day, everyone. First of all, I would like to apologise for the volume problem that occurred in the other lecture theatre. It evidently has a different setup. Apparently there's no problem in this one. So next week and onwards I'll make sure that it records properly in that theatre. For now, we're in this theatre, and I'm going to continue on a little bit in the vein that we were talking about on yesterday morning. Sorry. And that means deducing a little bit from the axioms. So first of all, it was right at the end, so I will restate the axioms of probability. And yesterday there was an introduction where I talked about the philosophy and why you might want various theories of probability. And long story short, if you want to summarize that, probability is essentially for objective experiments that can be repeated many times, it's the long-run frequency. That's the meaning of it. But many events can't be repeated many times. So there have to be various philosophical interpretations if you can't repeat your experiment, such as subjective likelihood, my belief, if you could repeat it, of what proportion of time it would happen, even though you can't repeat it independently. Another way of thinking about it would be if you had like multiple universe interpretations. Some physics is a bit like that, in what proportion of the cases would it happen. In any case, it has to have some interpretation, but it could be subjective. But in order to count as a probability function, it has to be consistent. And the biggest part of consistency is, well, anything at all happening has probability 1, that's certain. The empty set has probability 0. So those are the first, anything at all happening has probability 1. And all probabilities are non-negative, clearly, because they're frequencies, if you think about it that way, or proportions. And finally, that it has to be additive. So that's the real restriction that requires things to be consistent. You can't have a probability where I think the probability of rolling a die is, a half for 1, a half for 2, a half for 3, a half for 4, and so on, because it adds up to more than 1. So that's an example of the consistency. So once we drill down to these axioms of probability, they are enforcing nothing more than the consistency that I was talking about. Once you have that consistency, you can do a remarkable amount of mathematics just deducing from those. So I'll give them numbers. First of all was for all events. This was the same as the end of last lecture, but just spreading it out. The probability of that event is greater than or equal to 0. Okay. Secondly, that if now the lecture notes you'll see sometimes use the letter capital S for the sample space. That's fine. Sometimes S is a very common letter, so I'm going to use this capital omega, which will never ever mean anything other than the sample space. But you can use S for sample space. So the set of all outcomes is the sample space. So for those of you who've got what that means, that's the set of all possible outcomes omega. So that's a lowercase omega, by the way, not a W. Then these are conventional letters that make it easy to remember what we're talking about. The probability of that whole space is equal to 1. So it is certain that something in some outcome in the whole sample space will happen. And the third one, effectively the first two are pretty trivial. They're just saying it's a proportion between 0 and 1. The third one is the non-trivial additivity. So this is sometimes called countable additivity. If you're wondering, if ever I say the countable additivity. Okay. Now, countable, there was a question, does countable mean finite or infinite or possibly both? In my usage, probably possibly both, but in essence I'm going to write it for infinite countable sets. So that's sets that are in bijection with the whole natural numbers. So if A1, A2, A3, are pairwise disjoint events. I know that seems a complicated way to say it. By the way, that focus is not great, is it? I'll see what I can do the best with this. Record it. Okay, pairwise disjoint events. Seems complicated, but pairwise means every pair of them. So I and j are not the same. For every pair where I and j are not the same, then the intersection is the empty set. Then the probability of the union. I wrote it with the union symbol last time, but I'll just write it in ... form this time. It's the same, of course. You get it by adding them up. Now, it's important that they're disjoint. Clearly, otherwise you could just put the same event again and again, and the union of the same event is itself. So they have to be disjoint. A1, for this to be exactly true, plus P of A2, and plus ... Of course, that's important. Now, I seem to have stated it only for infinite families of sets. That's for the sake of economy. Economy means I don't want to write more axioms than I have to, but there are very simple consequences, so simple that they don't really have names, but we'll just to show that these axioms, which we said before, are really enough to conclude an awful lot of things. And if you were ever wondering what the events are, remember that events are always subsets of the sample space. Now, if you want to think that every subset of the sample space is an event, probably no harm will come to you most of the time. So you can just imagine that if you like. Technically, sometimes we want it to be less than all subsets of the sample space, and don't worry about it. But everything here is legitimate. Taking infinite unions, all finite unions, is legitimate, so long as it's countable, not an uncountable union. So countable means I can just write it out as a list. Taking countable intersections is also legitimate. Taking complements is also legitimate. So whenever you do that to any event, you get an event. And that's the family of events. Simple consequences. You'll note I didn't actually say that the probability of the empty set is 0, so you sort of have to... I want the probability of the empty set. Can anyone think, well, which axiom am I going to have to use to deduce that the probability of the empty set is 0? 3. 3 is actually the only axiom that says anything really non-trivial. The others are pretty basic. So 3 is our power axiom. And, sorry, I mean that in the colloquial sense. So clearly I'm just going to have to put in empty sets here to get this, right? That would be, on the one hand, okay, so using axiom 3, I'll just put a little 3 above it. Can you see that? By the way, this is not super great, is it? Legible at least. Tell me if you have problems with the document scanner. Okay, so it's probability of empty set plus probability of empty set plus ... By the way, is anyone a little squeamish with adding up infinitely many numbers there? I did say that it's a prerequisite to have taken a maths course. At least as an undergraduate, it's a prerequisite. And if you're a graduate, you can take care of yourself, but you do need to know at least something about differentiating, integrating, and series. So adding up infinitely many things is a series. In general, does the sum of a series necessarily exist? Just to review some maths. If it's an infinite series. Is there necessarily a meaningful sum of infinitely many numbers? No. Can anyone give me an example where there isn't? What's an example of a sum of numbers that doesn't make sense or doesn't converge to something? Anything will do.
Natural numbers?
Yeah, 1 plus 2 plus 3 plus 4. That's an interesting one. You get minus 1/12 if you interpret according to non-conventional summation. But forget about the minus 1/12. 1 plus 2 plus 3 plus 4, the partial sums of that don't converge to anything. You get, triangular numbers, 1, 3, 6, 10, etc. You're never converging to anything. Now, but arguably, I like to be a little more lenient with this, and this is, by the way, as I said, it's a non-measure theoretic course. We don't go into technicalities, but if I get rid of number 2, these are the axioms of a measure space, so it's very closely related. Now, and in measures, or in probability, it's important to think about infinity very often. And there's a very simple sense in which 1 plus 2 plus 3 plus 4, it doesn't converge to a real number, but it does go to infinity, positive infinity. You know, as the closer, you know, if you want to be above a certain level, you just add sufficiently many terms, and 1 plus 2 plus 3 plus 4 plus 5 will eventually get as high as you like. So that does, I'll say it tends to infinity. I won't use the word converge because converge means to something finite, but it tends to infinity. So are there any series where we could add them up and it tends to something that is not positive infinity and not negative infinity?
The summation of 1 over the square of natural numbers.
1 over the square of natural numbers. Yes, that tends to a finite limit. It's famous 1 over 1 plus 1 over 4 plus 1 over 9 famously converges to, anyone know? Yeah, lovely formula, quite many ways you can do it, related to trig and complex numbers, anything you like. But okay, so it has a finite value, whereas the harmonic series, 1 plus a half plus a third plus a quarter, is infinite. You know, sort of grows logarithmically in the number of terms you add. So, but that still seems to confirm the issue of having either a finite limit or positive infinity. Can someone give me an example where it doesn't have a finite limit and it also doesn't tend to positive infinity? You should have had at least one such example in your series class or calculus class. I want something that doesn't tend to infinity but also doesn't tend to a finite value or minus infinity. Something else. Just a list of numbers that when you try to add it up doesn't do any of those things. That is a good example, and the main reason that that will work, but there are simpler examples that will work. In fact, if you take sine of pi over 2 times x, that might be a simpler example because that's effectively 0, 1, 0, minus 1, 0, 1, 0, minus 1. The key feature is repetition or cycling. Sine of x, if you do real numbers, is not, if you do, if you do whole number multiples of 1, it's not actually periodic. But it's effectively, if you're constrained within a region, but you never tend to any particular point within that region, you always stay within that region. That's an example of a series that does not tend to infinity, does not tend to minus infinity, and does not have a finite limit. So those are the very bad kind of series that you can't get a hold on. But this can't be one of those bad series. Can anyone find... okay, not just empty sets. Regardless of what sets I put in here, I'm claiming that this is always a very, very good series. It either tends to a finite number or it tends to positive infinity. Well, okay, yeah. In fact, it's got to be less than or equal to 1. But say we forgot about axiom 2. Even without axiom 2, this still has to be... there's no possibility of something... I'm just saying that this series always makes sense to us. It either makes sense as a finite number or it makes sense as infinity. The reason is that there are no negative terms. Is that clear? If you don't have negative terms, then this is sometimes called the monotone bounded sequence theorem, but that's a fancy name for something very basic. The partial sums are always increasing. So they either increase to a finite limit or they increase to infinity. There's no funny business. So the point is, the series we're dealing with, until we get to expectation, which is a little harder, the series we're dealing with are all very, very simple. They're series of terms that are either 0 or positive. And that means we can actually say that I can just talk about the sum of that series, so long as I allow maybe it to be infinity. So there's no... so what is on the right-hand side here? This was a long pause to say that there's nothing illegitimate in the following thing that I'm going to do. Oh, I don't know how that happened. Sorry about that. Okay, there's nothing illegitimate in the following. If probability of the empty set is 0, which we believe, probability of the empty set is 0, right? Because then it will be 0 plus 0 plus 0 plus 0. If it's not 0, then, like, say I have even a small number, a millionth even, a very small number. If you're adding the same thing again and again, the partial sums just tend to infinity. So the sum of that series, we're happy to say it equals positive infinity. if probability of the empty set is not equal to 0. So pretty clearly that looks bad. We're going to say that that's a contradiction. Technically it doesn't straight away contradict any of the axioms, but it's pretty much in contradistinction to axiom 2, because this really gives us an upper bound on sets. So, but an easier way to see that without appealing to axiom 2 is just to say this left-hand side. What is the union of lots of empty sets? Empty set. There's nothing in it, so you take anything that lies in any of the empty sets, it's still an empty set. So the probability of the empty set. So if the probability of the empty set is 0, then if it's not 0, so either the probability of the empty set is 0 or it's actually infinity itself. And probabilities can't be infinity. That will be a consequence of our second consequence, which is that the probability of a difference, let's just say, remember I talked about differences of sets? When it's omega minus b, I just write b complement or b bar. But when it's any difference of sets, this is better be if you have a subset relationship. B is a subset of A, then the probability of A minus B is less than, at the moment I'll just say something simple. It's actually equal to probability of A minus probability of B. But I'll just say it's less than or equal to probability of A. And the reason of that is quite simple, because actually I don't even need this proviso, because if I'm just saying it's less than or equal to probability of A, I don't need the proviso that one is inside the other. Because this is true, because once again axiom 3 is our real axiom that gives good substantial consequences. Probability of A is equal to probability of A minus B. So these are the ones that are in A that are not in B, plus the probability of A intersect B, plus, I'll put in, technically, part 3 I haven't restricted to finite lists of sets yet, but so just to satisfy that technicality, I'll just put in lots of probability of empty sets. Because, I've just written A is a union of A minus B. This is a disjoint union. You can either be in A and not in B, or you can be in A and B, that's the intersection, A intersect B, or, I'm just going to put lots of empty sets on the end. This is boring stuff just to get through the minimum possible axioms so that I didn't have to put in extra assumptions. So that follows from axiom 3. So axiom 3 says that this is the case, and probability of A is equal to probability of A minus B plus all these other things. And remember that all probabilities are greater than or equal to 0. That's by axiom 1. Everyone remember that? So, so we've actually proved this boxed consequence, right? This is sometimes called probability is monotonic. That's a fancy word for if the event gets strictly larger, if it includes more outcomes, then the probability gets larger. Once again, a kind of obvious thing that you would expect, but we can deduce it from those 3 axioms. So, arguably I should have done consequence 2 first, but because I've got consequence 1, the point is we know the empty set, of course, is inside the whole sample space, so the probability of the empty set is less than or equal to the probability of the whole space, which is equal to 1 by axiom 2. I wish I had better lighting on this. Maybe that would... Okay. Now, I agree if you don't like this kind of stuff, it is kind of angels dancing on the head of a pin, and I will avoid it as much as possible. But I do want you to see that everything that we're going to prove, unlike when I just started, I gave heuristic justifications of what probability is. But from this point on, until I guess the end of week 7 or 8, everything we'll do will be deducible from these 3 axioms. So they are quite powerful. So this is an example. We won't do everything in this much detail. So probability is less than or equal to 1. Okay. In particular, okay. You see there were these 2 options. probability of the empty set with either 0 or plus infinity. So that option is not possible. In particular, the probability of the empty set is 0. Okay, phew. So we finally got that kind of obvious statement which wasn't listed among the axioms of probability, but now we have it. And I'll continue by saying another easy consequence now that we've got that is from axiom 3, which axiom 3 was stated as countably infinite additivity. We get also finite additivity, which was never in doubt, except I just feel the need to show that it does follow without explicitly stating, which is that if A1, A2, in particular, you often use it for just two sets, but you can use it up to n. You know, a finite number of pairwise disjoint sets. Reminder that means every pair of them has empty intersection. Then, okay, exactly what you'd expect. I'll write it back in this form. Union I equals 1 to n, that's a finite union of all the sets. Probability of that is equal to, okay, get my other pen. Probability of that union is equal to sum I equals 1 to n probability of AI. So disjoint union gets us up. Okay. So what about if it is not a disjoint union? So events A1, A2, and so on. Now, whether it's finite or countable, I won't make a big distinction anymore. It's the same either way. If you want to turn finite list into a countable list, you add empty sets at the end. So what about events that may not be disjoint? Okay, now at the moment I'm just angling for a intuitive response. Oh, sorry about that. Intuitive response from people. The probability of the union, I equals 1 to n of AI. I'd like to say something, but clearly there might be an overlap, so it shouldn't be equal to the sum. Any proposals? Less or equal to, because this would just have some overcounting, but it couldn't have undercounting. Every outcome that was in here is in at least one of those, but it might be in multiple, so it could have been overcounted. So this is less than or equal to sum equals 1 to n probability of AI. Now, it's almost obvious, but once again, just to get you in the practice of going in a formal setting and going through the axioms, need to apply axiom 3, and you want to come up with disjoint sets. Okay? I'll call them events, but of course events are subsets of the whole sample space. Oh dear, too many buttons on this. What do I do? Stick up here until I can figure out what to do. And sorry about that. Okay, you're getting the point. We're doing things in quite some detail. Disjoint events, and clearly the AIs are not disjoint, so let's call them B1, B2, B3. We just want to apply 3, and to do that you have to come up with disjoint events. So any suggestions? I want the union to be the same. Let's start with A1. I mean, there are many ways to do it. It's far from unique. We'll start with A1, but I want to do B2, and I want to get extra stuff, but hopefully A2, but I can't overlap with A1. So there's a natural choice. Remember that you're allowed to subtract sets with this funny notation. By the way, subtracting A minus B is the same as A intersects B complement. I'll even put that in the side here in case. If you have a universal set, then this is equal to A intersects B complement, and we're often putting an overlap, a line over the top for complement, even though I don't really like that. But B bar will mean the complement of B in our universal set, which is omega, complement of B in the sample space. So if you're in A and not in B, clearly that's the same as this. So just remembering that. Anyone have a suggestion for B2? I'll draw a Venn diagram. That always helps people get their thoughts flowing. I'll only do 3, but you could have as many as you like. The Venn diagrams get worse unless you have higher dimensions. Interestingly, I think if you have n dimensions for your Venn diagram, which you usually don't, then you can manage n plus 1 sets and get all the relevant intersections. But mostly we do 2-dimensional Venn diagrams, so you can't show all the intersections unless you only have 3 sets. So here's A1, A2, and A3. I already kind of gazumped all of A1. So this stuff's taken, and I'm trying to be super... well, I have to be disjoint. There's no ifs or buts about it. So what would be B something? B2B. Yeah, I want to get everything that's in A2, but I'm not allowed to overlap. So let's do everything that's in A2 that wasn't already in A1. B2, A2 minus A1. Okay? You can, just so you get used to this, you could write it A2 intersect A1 complement. And I'm even going to use this horrible notation where you omit the intersection sign, just because that sometimes happens in the notes. But if you don't like that, you can put an intersect in the middle. Okay, so B3 suggestion. So we've got A1s there. A2 is this kind of crescent moon. What about B3? Not allowed to overlap. Anyone?
B3 minus A1 union.
Yeah. I don't want anything in A1 or A2, so you subtract the union. Now, of course, by De Morgan's laws, remember when you do, that's A3 intersect the complement, and complement of a union is the intersection of the complements. So A1 complement intersect A2 complement. So that's a little exercise in De Morgan's laws, but I think that those are sometimes overestimated as laws. If you just think logically, if you're in A3 and you're not in any of the earliers, then that's exactly what you're in that triple intersection. So, etc. So I'll give the general formula if you like. BK is going to be AK minus everything that was anywhere before that. A1 union A2 union AK minus 1. So this is one way. You could do others, but this is kind of the natural thing. You always want to get the extra elements from AK that weren't already there. Then it is obvious that the union I equals 1 to n of BI is equal to... I'm not even going to do up to n. I could do it to infinity, but you could do it to up to n as well. It would be exactly the same. BI equals union I equals 1 to infinity of AI. And probability of 1 to infinity of AI. Well, that's what we're interested in, but I have to relate it to BI. Probability of 1 to infinity BI. So that just follows from the previous line. And now I wasn't allowed to apply axiom 3 to that one, but the whole point of B is that I am now allowed to apply axiom 3 to this guy. Probability, sorry, that's now a sum of probabilities. Sum I equals 1 to infinity, probability of BI. A reminder that you should never have any hesitation of writing a summation sign if the summands are all non-negative. There's nothing that can go wrong. Well, the only thing that could go wrong, in theory, you could get in a value that is positive infinity, but that's really not so bad, something that tends to positive infinity. And in reality, this will not tend to positive infinity. This will be the sum of probability of BI. I want to relate sum of probability of BI to sum of probability of AI. This claim is that it's less than or equal to sum I equals 1 to infinity of probability of AI. Okay? So that's the conclusion that we want, and I better just justify that last line. Any takers for the justification of the last line? Just going from the sum of probability BI's, I'm claiming it's less than the sum of probability AI's. if I saying one series is less than another series, one of the easiest ways to say that would be to compare them term by term. And are they term by term in the correct order? Like, is probability of BI less than probability of AI? Yeah, it is. BI less than or equal to probability of AI. And that in turn is true because, so this is kind of reasoning is unwrapping backwards, but that's because this, and this is because BI is a subset of AI. It's AI minus something, so it's certainly a subset. And we had a little justification earlier that, on the previous slide, one of our first consequences of the axioms was that nested sets have nested probabilities. That was dressed up in fancy language as the monotonicity of probability. So now I'm going to switch, I think, to the slides, because there's a whole lot of other consequences, but I think we've done the main ones. And I have to... Okay, so I've got this ready, but okay, just for the moment I can finish off here. So there is a nesting. Now, the final thing actually I want to do before we get to the slides is, this is all very well, but it's an inequality. So what about if I want an equality? I won't try and do that in the infinite case. So let's try and get, you see, okay, so this was a proof. The latest thing that we proved was this relation, right? But this is, did I state it for... Yeah, I stated it for summing up to, union up to n, and now it's true both for finite and infinite, but I might as well state it for infinite because it seems more general. So, sorry, I'll change the statement of that. That's what I proved anyway. I proved the statement for infinitely many sets. Also true for finitely many. Now, for finitely many, I can do better than just saying less than or equal to. I can give an exact formula. So this one even has a name. It's called the principle of inclusion and exclusion. Or sometimes people just say inclusion, exclusion without the word principle. So, so for any, these can be any events you like, but I'm only going to state it for finitely many of them. A1, A2, A3. Here's the statement. You know, I want something, up to AN, so finitely many. Okay, probability of A1 union all of these events. Okay, I'm going to start it, so, and there are two ways to write this. One is with various sum-ands with subscripts and so on. One of them is with dot, dot, dots, and hoping you understand the dot, dot, dots. I'm going to do the latter. And we'll come back to this later because there's a quick proof of this that can only be given once we've talked about expectations. So, for the moment, I'm just going to allude to the fact for you that we can say more than the probability of the union. These don't have to be disjoint, of course. The probability of the union, we can say more than that's less than the sum. I can give the correction. So probability of A1 plus probability of A2. Okay, so you see I've become a bit lazy. I'll often just use the letter P rather than a fancy P for probability. I think you'll manage. So it's that. That would be the case if it was disjoint. I now have to do corrections. And the corrections are kind of sort of what you'd expect. I'll even draw a Venn diagram. It's always just a good... okay. Once again, this is only 3, but it works for n. If I've added everything up here, then anything that's in 2 of them has been double counted. So it makes perfect sense to subtract everything that was in an intersection. When I say it's in 2 of them, I mean it's in both of 2 of them. Minus probability of A1 intersect A3 minus dot, dot, dot. Now, you'll just forgive me, this is not an infinite dot to dot, it's just every pair. They have to be not the same, not A1 intersect A1, just every pair that's not the same. And you don't count, of course, A1 intersect A2 is just one pair. You don't do A2 intersect A1 as well. You only count, you just remove the pair once. So I just won't flesh all those out. But then, here's the problem. If there were only pairs, that's fine. And anything that was in only 2 of them would have been counted correctly. But anything that was in 3 of them would have actually been counted 3 times positively, 3 times negatively. So you need to add it back on. So that's plus probability of just all triples. So A1, A2, A3. And lest anyone think there's anything cyclic or anything like that going on. It's absolutely not cyclic, it's all triples. So A1, A2, A4. I'm just trying to do all the triples in some kind of tolerable order. So first 1, 2, 3, 1, 2, 4, okay? But all triples. So in case it wasn't clear, I'll just write above all pairs, all triples, okay? And if that were 3, that would be all of it, but so probability of A. Okay, so now you get the pattern, it's all quadruples. A3, A4 minus dot dot dot. Okay, so all quadruples. Okay. You have to do everything intermediate plus dot dot dot. So clearly this is the nicest formula when n equals 2. When n equals 1 doesn't tell you anything. When n equals 2, this is nice. Probably A1 plus A2 minus probability of the intersection. When it's 3, it's also quite nice. There's only 7 terms, but it gets bigger and bigger. There's always 2 to the n minus 1 terms, actually, if there's n. You know, it's every subset except the empty subset. So, and then plus, I'd better say it's minus 1 to the power n minus 1 probability of A. So this is all n tuples. There's actually only one n tuple, which is A1 intersect A2. This is in everything. Intersect AN. So that is the unique n tuple. So as you can imagine, for such a complicated formula, different authors write it in different ways and so on, but this is no summation science, just clearest as I can what's going on. Now, okay, I'm not actually going to give you any proof, and to assuage the guilt, I'll say proofs. You know, induction. Anyone who likes induction can go nuts. I don't. So another proof. So this is kind of, I mean, there'll be some in the textbook, there should be some in the notes. And I'll give one later once we've done expectation, but we haven't done expectation yet. Another one is just count how many times each outcome. Now, technically you should work on bigger steps than outcomes, but, you know, is included in right-hand side. That's kind of a good way to do it, because you just, like, anything that's in only a single set is just counted once here. Anything that's in 2 is counted twice here, minus once there. So you can do that using expectation. So we haven't done expectation yet, so that's a convenient dodge so that I can dodge doing that later. So that's one of the biggest consequences of the axioms. It requires a bit more work for now. We've done some basic ones. And at that, okay, so I'll just leave this up there for a moment. So I will go back to slides. There's a lot more humdrum stuff that I want to get through a bit quicker, so I'll go back to slides. Any more questions about the axioms or the principle of inclusion-exclusion or any of the other consequences we did? No? Okay, so now we'll go to slides. Oh, did they? Doing this well. Okay. Plan B. Plan B, manual slides. This is better because I can annotate them. So, okay. So a review of basic set theory. Okay, I'll zoom in a bit. Okay, we talked about all this empty universal set, complement written with an overline, subset, intersection, union. So I think, okay, this is, I really dislike that, so I'm going to change that to a set minus sign. That should be a slanted thing, because sometimes you actually want to subtract the elements of one set from the elements of another set as numbers, and that's something totally different. So, yeah, set minus is different from normal ones. Okay, so proper subsetting. Okay, we never talk about proper subset, but that would just mean that you know, it's not equal to the same set. Disjoint has no elements in common, and I used the word pairwise disjoint when you have multiple. It's not just saying there's no elements in common to all n. It's saying that every pair of them has no elements in common. Venn diagrams. Okay, so this stuff we're going to get through very quickly. You will have seen these lecture notes on the website anyway. That's a total example. We've done Venn diagrams. Algebra of sets. It's true I didn't emphasize all of these. I emphasized De Morgan's laws. A complement turns the union into an intersection and an intersection into a union. These are kind of obvious. So commutative, associative, and distributive. You would be familiar with them with arithmetic. In arithmetic, multiply and multiplication and addition are both commutative and associative. And in addition, the word used is addition distributes over multiplication. So distributive law says AB plus C is equal to AB plus AC. We've taken an addition and we have distributed it over the multiplication. So that's the word that's used is addition distributes over multiplication, but not vice versa. Easy to check. By contrast with sets, it distributes both ways. So union distributes over intersection, intersection distributes over union. I'll let you verify it if you want. It's just basic logic about what elements are in which things. So this can be useful when you just have a whole list of sets and you're trying to simplify. You can turn A union B intersect C into an intersection of two unions, or vice versa. Okay, De Morgan's laws, illustrations. It's really totally obvious via logic, so I'm not going to go through that so much. You can write out, okay, so the logic of it would be take any element in one of them, check that it's in the other. Take any element in the right-hand side, check that it's in the left-hand side. Kind of slow stuff. Okay. Yeah, second, by the way, the De Morgan's laws, you know that complementing twice gets you back to where you are. If you're in set A, then you're not in set A. If you're not in set A, then you were in A to begin with. So double complement is the same as the original set. And therefore, you just apply complement of A complement union B complement. If you do, you get double complements of both of them, so that's the intersection. So yeah, they're all related that way. There's a duality between unions and intersections, and the duality is achieved just by taking complements. Okay, events expressed as sets. This is some more concrete stuff. I've been stating everything in great generality because it turns out the kind of probability where you just list out all outcomes and give each of them a probability as a singleton set, that is a very limited view of probability. It chokes at even the first sign of anything tricky, including flipping a coin infinitely many times. What are the outcomes? They're infinite strings. So while you can think about doing a sample space as just a finite, this is really the most basic sort, and it's not representative of most of the problems we're doing. As soon as you have a continuous random variable, or as soon as you have infinitely many coin flips, which you often do, then you're in a more complicated setting. Nevertheless, if the outcomes are just a simple set, then you can just say that. And then you can write the events literally as a set of elements. Okay, but once again, probabilities exist of events, not of outcomes. The singleton outcome is an event, but you need to have probabilities of other larger events too. Okay, 3 axioms of probability. Luckily, I got the numbering the same. Okay, there's no true version of that, but yeah, axiom 3 is the big one. I guess that's natural. Okay, so for dice, by the way, whenever I say a fair die, I mean 1, 2, 3, 4, 5, 6 have equal chance. And whenever although you could do an n-sided die as well. Whenever I say a fair coin, I mean heads and tails have equal probability. Okay. Yeah, so technically, of course, you're doing P of a set, so you put the set brackets around it. But no one's going to mind if you write P of a single element. It's clear what's meant. P of the singleton set. Okay, so getting through this quite quickly. So some consequences, see, it's quite grandiose here. We call them theorems. I will have done most of these. Yep, so we did that both ways. I would even quibble with this proof, because subtracting P of omega from both sides, not P of omega, P of the empty set, this is invalid because, not to criticise the notes too much, but it's invalid because if you have something that equals positive infinity, you can't just subtract positive infinity from it and get 0. It's totally invalid because, for instance, like if I add up, 1 plus 1 plus 1 plus 1, I get infinity. If I add up the same thing incremented by a geometric series, I get sort of infinity plus 1. And then I would do infinity minus infinity and I would get 0, but actually I should get 1. So the point is you can't, so wrong. Okay, 0 marks. Second, but our proof was correct. Theorem 2, axiom 3 also holds for finite sequences. By the way, I didn't write these notes, but that's all right. There aren't many errors in them, and it doesn't really matter here because we're just doing angels on a head of a pin sort of stuff. Okay, axiom 3 also holds for finite sequences. We did this once you had AR equals 0. Probability of a complement equals 1 minus probability of A. I guess I didn't exactly do that, but of course it follows because you just divide the whole space. Of course, S is equal to omega in our parlance. That's the whole sample space. Sample space is everything in the set A. So either event A happens, which is A, or event A does not happen, which is A complement. Those are disjoint. You can't both happen and not happen at the same time. So it's 1, the probability of the whole sample space, is the probability of the event plus the probability of its complement. Therefore, complements, take the complementary event, you get 1 minus the original probability. Okay, probability of A at most 1. That's a subset. I of course said that probability of A is a subset, is less than or equal to probability of B whenever, so this is a more general statement that I said that A is a subset of B. Okay. Another way of saying that was that for any sets at all, A intersect B is going to be less than or equal to the probability of B. And indeed, less than or equal to the probability of A. Okay. That's right here. Same proof. Okay. Many other such results we could write down and prove. That certainly is true. I might even give you one or two in tutorials, but it's not really a super proof-focused course. It's more that you see a full setup of probability and you are able to do calculations that involve some more complicated probabilistic setups. But as I say, the interest of probability theory is not really going from the minimal set of axioms to bigger statements. It's in what you can actually describe about the real world. So that's why we will not do endless problems like that, but we might do a few more. Sample point method. Once again, I would say that this is kind of baby probability because it's probability when you have only a finite number of outcomes, and that's really quite limited. You would have done it at school probably. You would have said something like probability equals number of favourable outcomes divided by number of total outcomes. That's even more baby because each one has the same probability. So there's no need to assume that every outcome is equally probable. If you do, then it's just number of outcomes divided by the total. But even if you have a finite set of points, you just assign them a set of probabilities that add to 1. This is really quite easy. And then P of a set is, of course, the sum of the probabilities of each of the singletons. So if you can do that, good. Most problems you can't do that. Okay. But so anything that involves a fixed finite number of rolls of a die or a fixed finite number of coin flips, you will be able to do by this method, if laboriously, because if you have 10 coin flips, that's 1024 outcomes. So it quickly becomes unpleasant to do this, even if you can do it. So there's a need for better methods, but nevertheless, the sample point method exists, and it says list all the sample points. So quite basic. Okay, so but for 2 tosses of a fair coin, quite feasible because there's only 4 outcomes: HT, HH, TH, TT, and each of them has probability 1/4. And by the way, this hasn't been sort of elaborated too much. You're sort of thinking each outcome should have the same probability. In essence, what's going on there is because the coin flips are independent, one has no influence on the other, and that's why HT has the same probability of HH. If you didn't know they were independent, for instance, imagine quantum mechanically entangled coins. I don't know, this is not possible, but imagine coins that somehow magically, I flip one here and another guy flips one in New York, and they magically always land on the same side. Or they might be entangled oppositely, so when mine lands heads, his always lands tails, and when mine lands tails, his always lands heads. Then there's the same 4 outcomes, HT, TH, HH, TT, but they might not all be probability 1/4. You might get probability 1/2 for HH and TT, and you might get probability 0 for HT and TH. That's if there's entanglement. So it's not a physics class, so the point is, if you don't know that they're independent, if you don't know that one experiment has no influence on the other, then all outcomes are not going to be equally probable. You don't just multiply probabilities. So really, independence is the key as to why that was recommended. Okay, A is going to be that one head comes up. Okay, so it's HT or TH. You add up the points. As I say, this is a really baby way to do it. So so when sample points are equally likely, you do number divided by number. When they're not equally likely, you have to add up probabilities. Okay, 2 heads on 3 tosses of a coin. Once again, there's a lot better ways of doing this, rather than listing out all 8. So that's why we're getting on to combinatorics. Yeah, counting sample points. So counting tools. Now, once again, many of you will have done this at school, so we'll do it rather quickly. Ordered pairs are the easiest. A comma B is different from B comma A. That's why it's an ordered pair. And if you do that, you have maybe M choices for A, N choices for B. You have M times N choices for A, B. There's no relation between the two. So you multiply if there's no relation between the two choices. Whereas if you had a relation, for instance, if you're, not allowed to have them the same, that would be a bit more complicated. You'd have to subtract. So if totally independent choices, you multiply. That's the MN rule. Factorials. Well, here's the thing. If you want a permutation, okay, a permutation is another word for the number of distinct possible arrangements of n objects in a row. So that's another word of that is permutation. A full permutation. A partial permutation is when you only arrange some of them, but a full permutation, you arrange all of them. N choices for the first one. Now, it's true that they're not independent because you can't put the same object in first place and second place. They're not independent. But still, a little, if you warp your mind around the MN rule a bit, you still just abstract over which exact... You take the first object, then you abstract